Okay, the ellipse is different from the hyperbola. What we're going to be doing is hyperbola looks very much the same here, but what you'll notice right there is we have a minus sign in this equation. So really, it's like an ellipse, but it's the set of all the points in a plane whose distance is the difference between two foci, instead of the sum between the two foci that remains constant. Like in the ellipse, which had a plus sign there, the hyperbola has a minus sign there. Now, another difference, the ellipse had a major and a minor axis. We don't have that with the hyperbola. We have a transverse axis, and we have asymptotes. We have vertices and foci in a center still, but we don't have a major or minor axis. We have a transverse axis. So one of the things you should also notice is that a squared is still first both times here. It's x squared or y squared that's first that's now different, and that has to do with the minus sign being there. So here's how you determine whether you're vertically oriented or horizontally oriented. It has to do with who's first, x squared or y squared. We're going to get to that in just a moment. Now, what we're going to find out here is that what goes on is we're going to find our foci is still the distance A goes out the transverse axis, and C goes out to the foci. This time, C is found not by c squared equals a squared minus b squared, but a squared plus b squared. So this is actually back to the Pythagorean theorem, or at least the way that we remember it. So here's one way I remember it. The equation with the minus uses the equation with the plus. The one that had the plus here had the minus there. So the first thing we're going to do is we're going to figure out how to find our vertices. So let's take an example problem. Let's go ahead and say we've got x squared over 9 minus y squared over, I don't know, let's say 4 equals 1. So there's our standard form. It's going to be centered at the origin. And since a is always first, we can see that a squared is 9, so a equals plus and minus 3. Over here, b squared equals 4, so b equals plus or minus 2. We'll see how to use part b in a little while. For right now, a is 3. That's the distance of our transverse axis. So, how do we deal with that? Which way is which? Well, when x is first, that's when we're going to go ahead and have our transverse axis go parallel with the x-axis. When y is first, it's going to go parallel with the y-axis. So in this case, x is first, so our transverse axis goes parallel with the x-axis. So we're going to go minus 3 units here and plus 3 units there. Then, what we're going to do is we're going to use this equation here to determine the c value out to the foci. So c squared equals a squared, which we see as 9, plus b squared, which is 4, which equals, 13. So c equals approximately plus or minus the square root of 13. And if we use our calculator really quickly, we find that the square root of 13 is approximately 3.6. So I'll put that in there, 3.6, which means if we go out 1, 2, 3.6, there's a focus, 3.6, there's a focus. And now the shape of the hyperbola actually looks like this. Something, and it kind of looks like it's a parabola, but it's not. There's going to be one key difference we're going to see in a little while. And that's going to have to do with this b value combined with the a value. So first of all, I just wanted to show you that's how we find the vertices and the foci. So what we want to find next are the asymptotes. And there's two ways to do it. One way is to use the equations. And using the equations, we realize here that the asymptotes are y equals plus or minus b over a x, or y equals plus or minus a over b x. So what that really is a y equals mx plus b equation with a y-intercept of 0. There's plus nothing. So there's going to be our y-intercept right there. And so then what we realize is determined by which equation we have is going to determine which of these would work. Now, what I always use is what we call the box method. And the box method uses A and B. And what we do is we go out A to find our vertices, but like the minor axis of the ellipse, we're going to do B as well. And so that's going to go plus 2 and minus 2. And then what we do is if we draw a dashed box, rectangle really, going through the two vertices and the two B values, we get that. And what we do with that is we end up getting an asymptote. You can see it. So my slope's going to go right like that. And then right like that. And really, those asymptotes show where my graph really should be approaching, but never touching. So my graph, to get a little better, it's closer and closer to this. So unlike a sideways parabola, which gets steeper and steeper, this gets straighter and straighter. So it is different from a parabola. Whereas a parabola would do something a bit more like this. Remember, a parabola going this way goes like that. Going sideways would be more like that. So it's getting more and more steep or flat, depending on the orientation, if you will. Whereas a hyperbola is not. It's going just towards these asymptotes. So what we figured out here is how to find the vertices, which is the distance A from the center. So I'm going to go ahead and label this is A, right there. And then out to the foci, this distance is C. And then going up here, that's B. So if you have A and B, you can find C using our equation here, which resembles the Pythagorean theorem. And that's what we've got so far. Next, we're going to see how to go ahead and write equations knowing the graph or knowing some of the information. So I'll see you in just a moment.